In 1977, three chemists Shirakawa Hideki, Alan McDermott, and Alan Heger found that iodine-doped, oxidized polyethylene possessed great conductivity, making them awarded the Nobel Prize of Chemistry in the year of 2000. However, polyethylene is hardly used in electronic devices or electron-proof coating that we use today. Rather, several new polymer materials are used instead of it, like PDOT, PSS, PANI, and PPY. Well, how did that happen? Hello guys, this is Charlie Yang from MSE of NTHU, and in today's topic, the evolution of conductive polymers, we are going to talk about why polyethylene is not used in modern technology and what have we done to make conductive polymers meet our practical needs. Okay, before we start, let's talk about conductive polyethylene first. So most polymers are good insulators. They do not possess electrons like metals, and they do not possess holes and free electrons like semiconductors either. So how do we make polymers that can conduct electricity? Looking at the structure of non-conductive polymers, it's not hard to see that they all have conjugated double bonds or aromatic metals that create conjugated double bonds. And these pi bonds are exactly the key to unlocking conductivity of polymers. But the pi bonds on these polymers are still very hard to delocalize, which means they cannot move easily and thus they can't produce significant electric flow just on their own. Remember that we said that the first ever conductive polyethylene are iodine-doped and oxidized. That's right, these polymers are required to undergo the process of doping, a process that removes electrons of pi bonds by oxidation and reduction reaction. By undergoing this process, the pi bonds on the chain are easily delocalized and become able to conduct electricity well. So for now, we might ask how good its conductivity is exactly. A well-fabricated conductive polyethylene can have its conductivity as high as copper. Yeah, that's outstanding. Other conductive polymers' conductivity might not be as good as polyethylene, but they're still good enough to meet industrial needs. Then why don't we use polyethylene nowadays even with the fact that polyethylene has significant conductivity? Well, the main reason is that polyethylene is almost impossible to be put into practical applications. Here, we'll discuss why. First of all, polyethylene is extremely sensitive to moisture, oxygen, and light. It is known that unshielded polymers with only single carbon chain each other is vulnerable to the process called photooxidation, which is a process that turns oxygen gas and organic carbon bonds into free radicals and thus breaks the structure. And moisture can make this process even faster. Photooxidation process is especially significant in polyethylene, that in extreme cases, it can break down in minutes. Therefore, almost all the conductive polymers now contain chains with aromatic rings, which are proven to stabilize the polymers from photooxidation by resonance delocalization. Also, remember that we mentioned doping is needed for conductive polymers to work properly. Polyethylene is doped with iodine gas. Iodine grabs an electron from polyethylene to form triiodide ion. However, this reaction is unstable and will even degrade in inert gas condition. Also, imagine that you want to put polyethylene to practical use. You must prepare a tiny tube filled with iodine gas and polyethylene, which is, not practical at all. For the conductive polymers we use today, they are usually doped as soon as they are fabricated, which means the doping is stable. These doping techniques include finding stable dopants like putting PEDOT in PSS solution to form PEDOT-PSS, or making nitrogen atoms of aniline attached to acid protons to form PANI, etc. Now, before we start talking about the last reasons, let's think about a question. The glass transition temperature of polymers is definitely not as high as the melting temperature of normal conductors. So, will conductive polymers soften in real situations? Well, I believe you never saw your computer softening when it was in use. Glass transition temperature of polymers varies with their structures. Among the reasons that influence glass transition temperature, internal mobility, and stiffness of chain are of great importance. If the structure of polymer chains contains structure that hinder rotating or bending, glass transition temperature rises, and as you may realize, conductive polymers are hard to rotate and bend due to their double bonds and aromatic rings. In fact, it is hard to determine significant glass transition temperature for most conductive polymers. However, this also means conductive polymers cannot be shaped by normal means like extrusion, blow, and injection molding. Therefore, other approaches are used. Conductive polymers are usually reshaped by dissolving or sidechain processing. For example, PSS in PEDOT PSS can dissolve in water. P-adenine acids are organic acids like CSA or DBSA, so that it can dissolve in organic solvents. Polyethylene can be added by hexyl side chains to form P3HT, lowering its glass transition temperature significantly but still not affecting its practical uses. You might ask if polyethylene can be fixed by any of these methods. Unfortunately, the answer is no. Polyethylene shows zero solubility in almost all the solvents. Also, though we can add side chains to it, this makes its conductivity drop in a great amount. So, it'll be extremely rare to see conductive polymers made with polyethylene, and that's exactly why new materials are developed to overcome the cons of it. However, polyethylene still got its status in the field of conductive polymers. It is still the very first conductive polymers invented, given its historic status. Also, speaking of teaching how conductive polymers work, polyethylene is the one with the simplest structure and mechanism. In almost every introduction to conductive polymers, polyethylene is the first one to be pointed out. Furthermore, its invention even creates a model of solid theories, so no worries about polyethylene status. After all, no more is useless. And that's all for the video. Thanks for watching.